Okay, so hello everyone. Welcome to today's talk from Yuzhong Chen. Yuzhong is a fourth year PhD student in the School of Electrical and Computer Engineering at Cornell Tech, advised by Professor Mohammed. He's a visiting scholar at Stanford University under supervision of Terry Tembi, and his research focus is on algorithm hardware co-design for machine learning acceleration, with a special focus on quantization numerics, FPGA architectures, and processing memory. He's a finalist of the 2024 Qualcomm Innovation Fellowship. Okay, the mic is yours.
Yeah, thank you for the introduction, Professor Wu, and thank you again for inviting me. Uh, the title of my presentation is Efficient Algorithm Hardware Co-Design Methodology for Quantized LLM Acceleration today. So let me start with a very quick motivation. Yeah, so we know that the large language models, they are very popular. Like we know that ChatGPT, they got a record of 1 million users in just 5 days since it was first announced. And the open source Llama model from Meta, I think the first version, it got 10 million downloads in just 1 month, which is crazy. But the problem is that in order to deploy or run these LLMs, it can cost a lot. For example, you want to deploy ChatGPT in a data center, it can easily cost you $100,000 per day, or much more than that now. And even you want to just run a small open source Llama model on a commercial GPU, it can easily cost you more than $5,000 per device nowadays, and maybe even more if you want to buy a more advanced like Hopper or Blackwell GPU. So this big cost can lead to very high power and high latency, which are prohibitive for edge scenarios that are constrained by hardware resources and latency and power consumption. As a result, compressing large language models is very crucial for real-world edge scenarios, such as self-driving cars and personal assistants on our cell phone, and some cases where the user data is very sensitive. And one of the most popular and hardware-friendly techniques to reduce the cost of LLM is quantization. So we know that maybe NVIDIA has proposed a lot of quantization precision and formats during the last several years. And here I'm showing some of them. Because many quantization precision formats exist, we can assume that, or you may guess that there's a complicated trade-off between accuracy, memory, and compute efficiency. And I'll discuss some of them as I go through this slide. So for example, I think the early format, 8-bit integer, I'm using int 8 here. It has a sign bit and 7 mantissa bits. It has a range of minus 127 to plus 127. It was originally added in Turing, which was an early GPU architecture. But I think it's quite new. But if you go to look at the recent specification from the Rubin Vera GPU from NVIDIA, you'll see that the throughput of this int8 format is very low. It's actually like, I think, about maybe 1% compared to the throughput of FP8. So this FP8 format, 8-bit floating point, it has two variants. So one with a 5-bit exponent, 2-bit mantissa. Another has a 4-bit exponent and 3-bit mantissa. They have different dynamic range and precision. And this format was originally added in the Hopper GPU architecture. And if you go to look at the specification of Rubin Vera, so the compute throughput of this FP8 is about 100 times higher than int8. Because one reason you may guess is because of DeepSeek. So DeepSeek has shown that FP8 is very robust for LLM training, and it can significantly accelerate the pre-training speed, and you can save a lot of cost by reducing the time for large-scale pre-training. So I think that's one of the reasons why NVIDIA is almost giving up this int8 format, and by releasing those extra area, those int8 area can now be used for FP8 to improve the throughput of FP8. And another interesting case is 4-bit integer. It was originally added in Turing, but it was removed quite early. Like it was removed after Hopper. So even in Blackwell, you don't see this int8 format anymore. And instead, NVIDIA added this FP4, a 4-bit floating point format. It's actually called NVIDIA FP4. or in short, NVFP4. It was added in Blackwell, and NVIDIA also added this 6-bit floating point format. So it can also give you very high accuracy when you do pre-training or post-training quantization, and it can save the memory cost compared to FP8. But the 4-bit floating point format is currently, I will say, the lowest precision in NVIDIA's commercial GPU, and is like actively being investigated by both industry and academia for accelerating the pre-training and the post-training quantization of LLMs. So my research theme centers on unleashing the potential of edge machine learning through novel algorithm hardware co-design, with a special focus on quantization numerics, and previously also FPGA architectures, and more recently, processing in-memory architectures. I've done a lot of research to quantize the model acceleration, starting from conventional convolutional neural networks back to, I think, 2020 to 2022, and more recently about quantized large language model acceleration. So I have developed some early processing in DRAM architectures based on FPGA, and it was published at FCCM 2023 and FPD 2023. So the BRAMAC and M4 DRAM are the names of those two works. And I have also done some research about structured bit level sparsity. So basically using some bit level sparsity, which is this 0 and 1 for deep neural network acceleration, and it was published at Micro 2024, and the work was called BBS. And I have also proposed some new quantization data formats. So I have shown you a lot of quantization formats like FP8, Int8, FP4, FP6, but I have also done some research about new data formats that are not listed in my previous slide. So this work was called Bitmode, and it was published at HPC 2025. And I think the most recent work is currently under review by ISCA26, but is publicly available on archive, so you may go to read it also. And that's why I think recording is not a problem, although it's under review. So it's basically a heterogeneous architecture based on neural processing units, NPU, and processing in memory PIM. And it was called P3LLM. So basically it leverages mixed precision quantization for LLM acceleration using a hybrid numerical format. I will discuss more details later, but today's presentation is going to focus on two works, Bitmode and P3LLM. And they are actually a very hot research topic, which is the algorithm hardware co-design methodology for quantized LLM acceleration. This LLM, so here I want to mention that this LLM doesn't really refer to large language model. You can think it like as a wider scope. For example, like people now, they deploy vision language action model for self-driving, for robotics. They also deploy a lot of vision language models. They are all part of the LLM variants, in my opinion. So some of the techniques I proposed, also I use LLM to evaluate them, but they can also be applied potentially to other variants, such as VRM and VRA models. Yeah, so the first work I'm going to discuss is called Bitmode, a bit serial mixture of data type LLM acceleration. It was originally published at HPC 2025, and this is a joint collaboration with Microsoft Research and Imperial College London. So the idea of Bitmode comes from a novel quantization data format, as well as a co-designed accelerator. So I'm going to first describe the new data format. And it can be described in just a few sentences. It's very simple. If you look at this figure, I'm showing you the conventional 4-bit integer format from -8 to 7 if you use two's complement representation, as well as the 4-bit floating point format from -6 to 6. So if you look at this figure, you will notice that there is a -0, which is this red dot, and it exists in the 4-bit floating point format, but it's redundant. So the reason is that FP4 employs the sign magnitude representation. And if you use, for example, 1's complement sign magnitude representation for int4, you will basically remove this -8 value from this list, and it will only contain values from -7 to 7. And similar story for FP4. It contains value from -6 and 6. It's a symmetric data type, but because it uses sign magnitude representation with a sign bit, it inevitably introduces both positive 0 and negative 0. And of course, one of them is redundant because we don't need two zeros. So the idea of bit mode is basically to repurpose this redundant zero to a special computable value. So here I'm showing you that this negative zero, it can be remapped to 2.5, 5, and 8, and also the minus part. And it's actually a very small improvement if you think it from a quantization value perspective, because it's just a one value out of the 16 representable values. So why is it important? So we make this very novel by just allowing this negative zero to be reconfigurable. So what we do is that first we want to say we can replace this negative zero with some predefined special values called SV here. So if you look at this hardware, when we receive FP4 data, we will first compare it with negative zero. And if they are equal, we will basically decode this negative zero value to one of the predefined special values. And for example, this special value can be +5, -5, +8, and -8. So you only need 4 registers to store this special value, and you can actually tune the special value because actually the state-of-the-art quantization methodology, they usually use a per group quantization. Basically, you quantize a group of maybe 16 values in NVFP4 or 32 values in MXFP4. If you are familiar with NVFP4 and MXFP4, basically you group a tensor into many groups, and a group size is usually very small. It's usually 16, 32, or 128. So you can basically say that for different groups, I may choose different special value such that they can minimize the quantization error. So how do we choose these special values? It's actually through profiling. And here I'm going to mainly talk about weight-only quantization. For activation quantization, it's a bit complicated, but we can also do that. It's actually a future work. So if we just assume weight-only quantization, we can do this profiling offline. And here, this figure, I'm showing the normalized quantization error when we add different special values. And here I'm using 2 special values as an example to the 3-bit floating point format. It's not FP4, but it's FP3. FP3 is even simpler. The basic values only contains 1, 2, 4 with the plus and minus values. And if you choose to, for example, add a special value ±6 on top of this basic FP3 values, you see that the quantization error, this middle blue bars, they can be reduced significantly compared to this baseline, this no SV. This is the baseline FP3 data format. And this baseline FP3 data format is actually has a larger quantization error, slightly larger quantization error compared to the simple 3-bit integer format, which are the first and the second bars for every model. And by just adding 2 special values ±6 on top of FP3, we can reduce the quantization error by about 1.25 times or 1.3 times. So this is because, for example, here it's about 1.3, and now your error, normalized quantization error becomes just a 1 by adding a special value of ±6. So this is good. And we follow the similar method to determine the special values for FP4. It actually should be ±5 and ±8 for all the llama models that we show here. But these values, please note that these values, they are reconfigurable. You don't need to set them as 5 or 8. Maybe you want to deploy Queen. You want to deploy Queen 3 model, and you find that, okay, I want a special value of ±7. You can also do that. As long as this special value, they satisfy some hardware constraints. And we have some hardware constraints, which is that the special values have to be integers. So why do we restrict the special value to integers? It's because as integers are very computationally efficient. If you want to represent the special value with an arbitrary maybe FP16 or BF16 value, then you still need to use the high precision floating point multiply accumulates units, which actually offsets the energy and the area benefits of low precision arithmetic. So we don't want to choose FP16 special values because we need to use FP16 or BF16 multiply accumulates units to handle that, which is very area and energy expensive. So by applying this bit mode quantization format, we compare with some previous famous data formats in the architecture community, like this ANT work was published at Micro 2022, and this OLIVE was published at ISCA 2023, and also this micro-scaling format, which is very famous if you are familiar with the LLM quantization research. So micro-scaling is very famous. Like, for example, the OpenAI GPT-OSS model released last August. It was natively quantized in MXFP4. So this was actually an open compute project 2023. It's actually a standard now. It's widely deployed by all the, I think, leading AI companies like Meta in their AI chip and also Microsoft in their AI chip. So by comparing this bit mode with the previous data type, we find that the bit mode can significantly reduce the perplexity of the quantized LLM. So this perplexity here is lower is better. It's different from accuracy. It's just a LLM performance metric, and lower is better. So here we see that the bit mode can significantly reduces this perplexity loss compared to the FP16 when we use bit mode for quantization instead of other formats such as OLIVE and ANT. And the improvement is much more pronounced when we use 3-bit weight quantization compared to 4-bit weight quantization. And in addition to using this basic bit mode data type for quantization, we also explore the possibility of combining bit mode with state-of-the-art quantization algorithms. If you do quantization research, maybe you are very familiar with this AWQ and OmniQuant. So the original algorithms in AWQ and OmniQuant, they just use the integer quantizer. Basically, for 4 bits, they use int4, and for 3 bits, they use int3. And by replacing this quantizer, this integer quantizers with our proposed bit mode quantizer, we see that we can further reduce the perplexity of the baseline AWQ and OmniQuant algorithms. So here the table shows that at 4 bits, bit mode can reduce the perplexity loss of AWQ and OmniQuant by 13% and 28%. And at 3 bits, the improvement is more pronounced. So this means that bit mode can really push the limits of the LLM quantization to a new state of the art, at least during the year of 2025 when I published this at HPC 2025. Maybe now there are better methods, but please keep in mind that bit mode is a quantization data type. And if you go to read some quantization algorithm papers in the AI conferences, they usually target the algorithmic innovation, like they optimize the quantization scaling factor, they do some transformations such as Hadamard rotation. But as long as they use integer data type for quantization in their baseline algorithm, we can always try to plug in our bit mode quantizer and see whether applying bit mode can further improve the LLM accuracy compared to using the baseline integer formats. And here I'm showing 2 examples by applying bit mode on top of AWQ and OmniQuant. And in addition to this enhanced bit mode data type, we also co-designed an accelerator because this bit mode data type, it was not supported by any existing hardware accelerator such as a GPU, TPU, or NPU. So here we are co-designing a prototype accelerator with an overall architecture of 4x4 tiles, and every this processing elements tile it contains 8x8 PEs. And they share a single output accumulator in FP32 to amortize the hardware cost. Because also we quantize everything to low precision, we still have the scaling factor, which means that we must convert our partial sum. After we perform maybe a per group dot product, we need to convert the partial sum to FP32 and accumulate the partial sum in FP32. So that's why here, different PEs, they must share a FP32 accumulator because the final result, the final output activation must be FP32. So the design target is slightly different from previous quantized LLM accelerator work because what we want to support is a diverse bit precision. So in addition to the 4-bit bit mode and 3-bit bit mode, we say that we also want to support 6-bit and 8-bit precision. Because if you go to look at the existing quantization methods, I don't think any post-training quantization algorithm can achieve no accuracy loss at 4-bit precision. they have some small accuracy loss, but they still lossy. And if you really want to achieve no accuracy loss, you have to switch to either 6-bit or 8-bit for weight quantization. And here we are saying that by designing a unified hardware architecture that can support different weight precision, it can enable a better trade-off between accuracy and efficiency. So the design target of the bit-mode accelerator is to support diverse weight precision in a unified hardware encoding. And as I mentioned, I want to support 4-bit, 6-bit, and 8-bit, and 3-bit also. So what we propose is a unified bit serial representation for different precision formats. So here, every number is decomposed into a sum of bit serial terms. And every bit serial terms, they will have like there are 4 terminologies. So the first one is sign, is the positive or negative, and exponent, mantissa, as well as a bit significance. Because if you do bit serial computing, for every bit serial term, it will have a significance, which is a power of 2. And the good news is that the int8 and int6 can be converted to this bit serial term representation using the standard Booth encoding. Yeah, if you are, I won't describe the detail, but you should study the Booth encoding during your undergrad digital electronics course or computer architecture course. And for this FP4 or FP3, we convert the bit mode format to a fixed point format first, followed by a leading one detector to extract the bit serial terms. So here is a very simple decoder block diagram, and the area cost of this decoder is actually very small. If you want to know more about the details, you can go to check out the bit mode paper. But the idea is that for every FP4 value in our bit mode format, we only have 2 bit serial terms with a bit significance of 0 and bit significance of 1, respectively. And the exponent of every bit serial term is 2 bits. The mantissa is 1 bit. So after determining the bit serial representation, we now want to design a processing element to compute the dot product between weight and activation. And we do have another design choice here, which is to maintain the activation at FP16 to minimize the accuracy loss. Because we target weight-only quantization, usually weight-only quantization can give you a better accuracy compared to weight activation quantization. So when we did the bit mode work, our design choice is to simply maintain activation at FP16 to minimize the accuracy loss. But if you, now it's 2026, we can, if you go to read the DeepSeek paper or any other, I think, Quantized LLM paper deployed by industry, they usually can quantize activation easily to FP8 without accuracy loss. So this will be slightly changed, but the idea is still the same. We use bit serial weights to do the dot product, and we use the bit parallel processing for activations, no matter they are FP16 or FP8. And the function of this processing element is to support a 4-way mixed precision dot product between bit serial weight terms and FP16 activations. So first, before going deeper with this processing element, I want to just give you a high-level overview of the potential throughput improvement of this PE over the conventional IP16 Mac unit. So this PE latency is proportional to the number of bit serial terms, as you can imagine. The more bit serial terms you have, the higher latency you have. And it requires 4 cycles to perform 4 multiply accumulate operations with the int8 weights, and 3 cycles, 2 cycles for 6-bit and 4-bit weights, respectively. And the important technical detail is that it has a similar area as the baseline FP16 Mac unit. So there's a 4-way mixed precision PE has a similar area as a FP16 PE. And if you do a simple mathematics calculation, you will notice that if we have the ISO compute area constraint, basically we have the fixed compute area budget, then we can put the same number of processing elements for bitmode PE and FP16 PE. But because we can use 3 cycles to perform 4 max with int6 weight, the throughput can be 1.33 times higher compared to the FP16 Mac units that can only do 1 Mac every cycle. And for the 4-bit bitmode weight, we can achieve 2 times higher throughput than the FP16 Mac unit. This is a potential improvement. And now let me go through the details of this mixed precision PE design. So the first stage is exponent and sign calculation. So we add the exponents between array activation and weight. Then we align the exponents by calculating the maximum exponent and the delta exponent. So we also calculate the sign of every product, which is just an XOR gate. And for the second stage is the bit serial dot product. We simply multiply the 1-bit wait mantissa by the activation mantissa. So the activation mantissa is 11 bits because it will include the hidden mantissa bit. And this multiplication is very simple. It's an AND gate because it's a bit serial multiplication. And this is followed by the shifting module and the negation module because we don't know whether this product is positive or negative. And this negation block is controlled by the sign of the multiplication. And this shifting block is controlled by the delta exponent. And after getting the parallel sum between the multiplication of the mantissa, we finally just use a group accumulator, which is actually a modified floating point accumulator to get the resulting mantissa and exponents of this accumulation results. So here I'm showing the speed up of the potential speed up of the bit mode accelerator compared to the baseline FP16 accelerator, as well as the two state-of-the-art accelerators, Ant and Olive, published at Micro and ISCA. And here I'm showing two versions for bit mode. The first one is lossless. This lossless means that we have no accuracy loss compared to the baseline FP16 LLM. This is achieved by using 6 bits for weight quantization. We can also use 8 bits, but we found that 6 bits is simply lossless. So that is better. And for this lossy, it means that we have very small accuracy loss, within 1% for downstream tasks. So this means that we can usually use 3-bit or 4-bit bit mode, depending on the model and the data set. And for Ant and Olive, they cannot be quantized to 4 bits because they are not as good as bit mode in terms of quantization error. So Ant and Olive, they usually adopt either 5 bits or even sometimes 6 bits, even for the lossy quantization. Yeah, so here I'm showing that on average, bit mode can achieve like 2.2 times speed up over the IP16 accelerator without loss in accuracy. And bit modes, they can also achieve 1.7 and 1.5 times speed up over Ant and Olive with very small accuracy loss. And here's a summary of the bit mode. It contains both the new data quantization data type and the accelerator code design. It's also open source on GitHub. So the new data type remaps the redundant -0 of FP4 and FP3 to some computable special values. And it can achieve better model accuracy than prior custom data types. And it can also improve the accuracy on top of prior software quantization algorithms. And the accelerator adopts a unified bit serial representation for diverse weight precision to enable a flexible trade-off between weight memory footprint and quantization accuracy. And it incorporates a mixed precision processing element for efficient dot products and achieve a speed up over prior LLM accelerators. The second work I'm going to discuss is called the P3 LLM. It's currently under review by ISCA 2026, and the result is expected to come out I think in less than 3 weeks. It basically talks about unlocking efficient processing in memory for edge LLM inference with hybrid quantization numerical format. It's a joint collaboration with KU Leuven and Stanford University. So just a high-level overview of the processing in memory. Processing in memory is actually commercially available at Samsung and SK Hynix, and they both propose a processing in memory architecture for efficient LLM decoding. And here I'm showing a high-level overview of the PIM architecture. So you have different bank groups in DRAM using DRAM cells, and you have for every bank group you have 4 banks, and for every bank you will have 1 PIM compute unit near the DRAM bank. And if you want to save the area, you can also propose that maybe I can share 2 banks. So here you can share bank 0 and bank 2 with 1 PCU instead of 2 PCUs to save the area cost of a PCU. And here you have a peripheral and global buffer. The global buffer can sense the input activation, or it can sense the attention score or query for the self-attention module to perform the dot product between the weight and KV cache stored in DRAM using this PCU. The PCU microarchitecture implementation is slightly different for Samsung and SK Hynix, but the function is the same. It's just a dot product. So for Samsung, it uses FP16 precision, but for SK Hynix, it is very customized. It's only customized for deep learning application because only deep learning can use BF16. If we want to target conventional applications with PIM, I guess you have to use FP16 because BF16 is still not a IEEE standard. And the implementation is also slightly different because Samsung adopts a SIMD, single instruction multiple data implementation for this PCU. And SK Hynix adopts just a reduction tree based dot product followed by FP32 accumulator. So you may imagine that the SK Hynix PCU will have a lower area because it only requires one FP32 accumulator. So this intermediate adder tree, they can have a smaller area. They are not implemented with the FP32 accumulator. But for Samsung, they must implement every data path with the FP32 accumulator because it's a SIMD, and the area is slightly higher compared to SK Hynix, but it has a much higher flexibility. So here I'm showing the limitations of this existing high precision PIM for LLM decoding because both Samsung and SK Hynix, they adopt 16-bit floating point representation for PCU design. And here I'm showing a roofline analysis of different operators on different accelerators. For operators, I'm basically referring to the linear layer with different batch size, such as this BS1 means a batch size of one linear layer, BS2 means a batch size of two linear layer. And this multi-head attention, MHA, group query attention, they are standard attention operators in recent LLMs. And for the group query attention, they have a hyperparameter called group size, which is a G here. If you are not familiar with GQA, you can also go to just read I think the GQA paper from Llama. I think it was adopted by Llama 3. Yeah, Llama 3. So I'm going to show the limitation of the existing HBM PIM as an example from Samsung. I'm going to show the limitation of HBM PIM as an example to demonstrate the limitation of high precision PIM for LLM decoding. So if we look at this roofline plot, we see that as the arithmetic intensity increases, NPU can become very efficient for batched LLM decoding and grouped query attention. Because for grouped query attention, when the group size becomes larger, such as 8 and 16, maybe even 32, if you do, in that case, I guess it will be called multi-query attention, but let's just use GQA for consistency. Then when we have very large group size for the GQA, this self-attention operation will become GEM even during decoding. So it means that the NPU can exploit data reuse because they only need to access the DRAM once, and then they can exploit the massive computational parallelism in the systolic array to just reuse this DRAM data in the cache, and they perform massive computation with very high performance. And the problem for HBM PIM is that it was originally designed only for single batch inference and multi-head attention. Because if we refer to the roofline plot here, we almost can only achieve performance benefits over NPU when the arithmetic intensity is less than 4. So here actually this crossing point is actually means arithmetic intensity of 4. This is because the internal PIM bandwidth is 4 times higher than the off-chip DRAM bandwidth in HBM PIM. So if your arithmetic intensity is 1 for single batch inference or multi-head attention, you can achieve ideally 4 times throughput improvements over the NPU for LLM decoding. But the problem is that like nowadays people are switching to GQA with a higher arithmetic intensity, and even you target edge LLM application. Sometimes you don't have a single user. Maybe you want to play a game with 4 users. Now you have a batch size of 4 because every user will have a different request. So this PIM throughput of HBM PIM is severely limited by the area and power in DRAM technology. So why can't we improve the throughput of this HBM PIM? Maybe like let's say the throughput, currently the compute roofline is this line. Maybe we can move it to here or maybe here, just with a higher computing throughput. Then we can always achieve a higher performance compared to this NPU because the NPU throughput is follow this. I think this is the degree of the maybe 30 degree. It's following this the black line. So if we do HBM PIM, maybe the roofline is higher. It can be here. The reason we cannot do this is that it's limited by the area cost in DRAM technology because the DRAM technology transistor is very expensive. Usually the transistor density in DRAM is 10 times lower compared to CMOS technology. If we put a lot of compute units in DRAM technology near the DRAM bank, we have to sacrifice a lot of area for the original DRAM storage, which is not what we want. So in both Samsung and SK Hynix, they only sacrifice, I think, up to 25% of the DRAM area for putting the PCU. So one way to resolve this is to, again, apply quantization. Because quantization allows us to do low precision arithmetic with a higher area and energy efficiency. And here, when we do quantization, we mainly focus on the decoder layer of the ARM. So here's an overview of the ARM architecture with the embedding table and the language modeling head for the classification head. So the main bottleneck comes from this decoder layer with this self-attention module and multi-layer perceptron module. So we want to apply quantization to reduce the memory footprint and the computational demand of the decoder layer such that we can perform low precision arithmetic in the processing memory architecture with a lower area cost of the PCU. So the first question is that what operands should we quantize in a large language model? And if you are familiar with the memory footprint breakdown of an ARM, you will see that, okay, for attention layer, I want to quantize the KV cache because KV cache can grow significantly when the context length becomes longer, even for edge application. And for linear layer, usually we will quantize only weight because weight dominates the memory cost. But if we want to do quantized computation, like we want to compute the GEM-M or GEM-V operation in the low precision, we also need to quantize the activation because a lower precision activation can reduce the computational cost of the arithmetic unit. So putting it together, we want to quantize weight, KV cache, and activation. This is actually a famous, very popular research area in the algorithm community. If you are familiar with this QSERV from MIT, and also I think there are other papers targeting weight, KV cache, and activation quantization, maybe Quorot from Microsoft, and I think there are other papers, maybe from OpenAI and Meta. But it's a very hot research topic. And here, basically, I'm saying that we want to apply a well-known quantization configuration. W4A KV4. It means 4-bit weight, 8-bit activation, and 4-bit KV cache, because this can balance the accuracy, memory footprint, and computational efficiency. We can also go further with W4A4 KV4 quantization, but usually it will cause significant accuracy loss, even using the state-of-the-art quantization methods. So the potential of P3 ARM comes from applying this W4A8 KV4 quantization. And here, actually, we have this P. This P means attention score. We also use 8-bit quantization for the attention score. I'm going to give more details later, but now let's just use this W4A8 KV4 terminology. So this roofline, this green roofline tells us that the P3M can significantly boost the PIM compute throughput via quantization because it can reduce the area and power cost of PIM compute units. It means that with the same compute area budget, now P3M, I can put more compute units within the same area, and it can increase my roofline so that for this large region, so until the arithmetic intensity reaches 32, I can always achieve better compute throughput or better like decoding throughput compared to NPU from an ideal roofline perspective, rather than like achieving only performance improvement when the arithmetic intensity of 1 for HBM PIM. So here I'm showing the decoding acceleration opportunities with P3AM. During the preview stage, I always compute my GEM-M in the NPU because for preview it's compute bound and PIM is not good at that. But during the decoding stage, I need to carefully partition the operator graph to NPU and PIM because PIM has very limited functionalities. It can almost only do GEM-V operation. And for some scalar operations that require vector units, we can either choose to do it on PIM with some additional vector units designed in DRAM technology, which is actually a bad choice, or we can just offload those operators to NPU and leverage the FP16 or FP32 vector units for scalar operations such as layer norm and softmax. So here, our design choice is that the NPU can perform scalar or vector operations such as rotary position embedding softmax in very high precision, even up to FP32. And the PIM, it will only perform the matrix multiplication operations in low precision. And now I'm showing the quantization algorithm of P3AM. It's actually very different from the QSERV algorithm from MIT. Here, I will first discuss the 4-bit KV cache quantization by showing the opportunity and challenge. And this is a profiling figure of the KV cache distribution in Llama 3.1 8 billion. I want to show you some distribution plots so that we can better understand what are the opportunities and what are the challenges. So the first figure is value cache, and the second figure is K cache after the rotary position embedding. So the first observation is that the value cache has no outliers, because if you look at this figure, there are no big values, and all these values, they are very small. This is a good news because it means that these values, they are very easy to quantize. And we simply apply direct 4-bit asymmetric integer quantization along this token head dimension. So why do we choose this dimension? Is because that during the decoding, we generate the value cache token by token. And by adopting quantization along the token head dimension, we can quantize every newly generated value cache immediately. The bad news is that the key cache has this very obvious channel-wise outliers. They are very hard to quantize because this outlier, they can increase the dynamic range, which is bad for quantization. So there are some prior solutions. This work is called KV-Quant from NeurIPS 2024. It's from Berkeley. It applies per channel quantization, which is what I circled using this green box. So it means that it will apply quantization along the channel dimension instead of along the token dimension. This is bad because you generate the key cache token by token during the decoding, but you want to quantize along the channel dimension. And you cannot basically calculate the scaling factor very efficiently. And what KV-Quant does is that it will need offline calibration to calculate the per channel scaling factor. And this per channel scaling factor will be fixed during runtime. And this can lead to overfitting because it requires a calibration data set, which is bad for LLM because LLM is designed to target a very wide range of applications. And if you use calibration, it may just overfit to your calibration data set. So our solution is that we want to perform per token quantization without the need for calibration. And our solution is very simple. We simply smooth every channel and apply per token head integer asymmetric quantization during decoding. Though the idea of the smooth is that during the prefill stage, we can record this per channel maximum as the smoothing factor. And this mathematics formula tells that we smooth every channel by dividing this whole red channel, for example, by its maximum absolute value. So that after this smoothing, we see that this red channel becomes something like this. It actually has a range between 0 and 1 because everything divided by the maximum is less than or equal to 1. So that if you look at this smooth plot, it's very easy to quantize now because it has no outlier anymore. And this smoothing is only less than 2% runtime overhead from a latency perspective. So it's a very good trade-off in terms of accuracy and latency. And here I'm showing again the perplexity loss. Lower is better before and after our dynamic key cache smoothing. So we have observed that this dynamic smooth can significantly reduce the perplexity loss. Without applying this dynamic smoothing, we have the perplexity of 5.58 for Llama 2 7 billion. And after applying the smoothing, we have a perplexity of 5.51, which is only 0.04 perplexity loss compared to the baseline FP16 model. And here I'm showing this pre-rope and post-rope quantization. So it's if you are interested in this difference, you can just go to refer to the KV-Quant paper that I showed just now. And after discussing the key cache, now let's talk about the weight quantization. It's very simple. We just reuse our published 4-bit bit mode data type for weight quantization. And I won't go into more details because it's already discussed. For activation, our solution is to apply FP8 quantization. So previous work, if you go to read the QServe paper, or maybe I think a SpinQuant or Quartz paper from Microsoft and Meta, they always use the integer quantization for activation. This is bad because activation also has outliers, and the integer is very bad for handling outliers. And instead, we want to use this FP8 format for activation quantization. And if you compare this perplexity loss with the FP16 baseline model, you see that the FP8 with a 4-bit exponent and 3-bit mantissa, it almost has no perplexity loss compared to the 8-bit integer quantization, even with Hadamard transformation. So here, actually, I think I'm showing the 8-bit integer quantization with some other optimization techniques such as Hadamard transformation. And the good news is that for FP8 quantization, we don't need any calibration and Hadamard transformation, which is very efficient and doesn't overfit to a calibration data set. The question is that all? Like we talked about the W4A8 KV4 quantization. Is that all for the algorithm? Actually, no, because we didn't talk about two important operands in the self-attention module, which is the query and the attention score. Because if we only quantize the KV cache, it means that we still maintain the query, and this P means the attention score in FP16. And this is bad, because if we use FP16 to represent this query and attention score, we need a high precision hardware to handle this query and attention score. Because what our PIM can support is only 8-bit activation of this linear layers. If we don't quantize this query and attention score to 8-bit, or at least to maybe to FP8, we have to just use NPU for this Q times KT and P times V, because our PIM units can only do 4-bit weight and 8-bit activation. And in the case of QKT and P times V, it means that our PIM can only do 4-bit KV cache and 8-bit query and attention score. If we don't quantize them, what we can do is to offload this operator to NPU and rely on the NPU FP16 MAC units for computation, which is not what we want, because we want to leverage the high bandwidth of PIM architecture for decoding. Yeah, so here, like we want to say that the P3AM also wants to quantize the query and the attention score in FP8, which is usually neglected by prior W4A8 KV4 quantization works. So for query, we just use the FP8 E4M3 format, the same as activation. And for attention score, it's slightly different. So the question is that do we really need FP16 for attention score? The answer is no. And the question, another question is that can we use FP8 hardware for attention score? The answer is yes. There are two observations if you are familiar with the numerics of AM inference. Because the attention score has a range between 0 and 1, this is because that the softmax normalization after the Q times KT will give you a attention score between 0 and 1. So your attention score cannot go beyond 1 because it's softmaxed. If you are familiar with the FP16 coding, you will notice that we only need 4-bit exponents to represent a numerical range of between 0 and 1. So this means that we can just remove this most significant exponent bit because it's actually always 0. If you go to check the binary encoding of your softmax of your attention score, this bit has to be 0. It cannot be 1, because if it's 1, it means that this decimal value will be larger than 1, which is not the case for attention score. And the second observation is that attention score is always positive because it is between 0 and 1. So we don't need this sign bit at all. So it means that we can drop the sign bit and the most significant exponent bit. And we only have the 4-bit exponents left and the 10-bit mantissa left. And when we do quantization to FP8, we simply round the 6-bit significant mantissa bit. And we have this FP8 E4M4 format, which is kind of different from the FP8 E4M3 format in activation, because activation is signed. It needs a sign bit to represent positive and negative values. But for FP8, we don't need the sign bits. For attention score, we don't need the sign bit. We can represent this attention score using a FP8 E4M4 format with one more mantissa bit and higher, the better numerical fidelity. And it's very easy to do this quantization operation because we only need to round the mantissa bits. The rounding is very hardware efficient operation. And putting all together, here I'm showing the quantized model perplexity of P3AM and prior work. So this Arkan is ISCA 2025 work, and this Chorus is a NeurIPS 2024 work, and this QOQ is MLSys 2025 work from MIT. So we see that the P3AM on average, it can achieve 1.39 times and 1.21 times better perplexity than Chorus and QOQ, which are the two really two state-of-the-art quantization algorithms in the AI conference that are very difficult to beat. So if you go to check the architecture conferences, if you are very careful, you will notice that not many architecture algorithms can beat the AI the algorithms in AI conferences, which is a bad news in my opinion, but that's true because I think the mindset of architecture of architects and the algorithm designers are very different. They focus on different things. But here we are really beating the state-of-the-art algorithms in AI conferences. And these are from very famous research groups. This is from Song Han's group at MIT, and this is from, I think, the GPTQ, the very famous GPTQ team. And also it's a collaboration with Microsoft. So apart from the quantization algorithm, I'm going to quickly go through the accelerator code design of P3M. It's just a functional units design at a high level. Because the original HBM PIM, it has 8 PCU per channel, and every PCU contains 16 FP16 MAC units. And for P3M, because we adopt the low precision arithmetic, we can put more multiply accumulate units under the same compute area. So here I can improve the number of multiply accumulate units by 4 times. It means I can put 64 MAC units per PCU, and I still use 8 PCU per channel. So the area and energy, if you look at this table, it shows that the P3M MAC unit is only 1.08 times larger compared to FP16 MAC units, basically 8% overhead. And if you consider the whole DRAM level overhead, the DRAM stack overhead is very small, it's tiny, it's actually negligible, 0.2% or something. And this energy is overhead is also very small because this, if you multiply this number by 4, it means that the energy overhead is only 4% compared to the FP16 MAC unit. And here I'm showing the accelerator speed up compared to the baseline NPU that uses FP16 for decoding. So here the speed up is only for decoding. I don't consider the prefill part because the prefill part is still down NPU. There's no speed up for the prefill part in our case. And for the decoding, we can achieve a higher throughput compared to the FP16 NPU and this HBM PIM and this echo from ISCA 2025. It also applies W4A, KB4 quantization, but using a very different mechanism. And this idea basically cannot be applied to PIM. If you are interested in why, you can just go read our P3M paper, which is available on archive. So to summarize, the P3M achieves this kind of speed up over these 3 state-of-the-art accelerators. And this P3M proposes a new quantization algorithm that quantizes different LLM operands using a hybrid numerical format instead of a uniform integer format. And it achieves better accuracy than prior quantization algorithms Quartz and QOQ. And this accelerator code design, it adopts a lightweight mixed precision MAC in the PIM compute unit, and it achieves a speed up over this prior LLM accelerators, HBM, PIM, and Echo. Yeah, I think yeah, that's all for my presentation, and I'm happy to take a lot of questions.
Okay, thank you for the great talk. So
Thank you.
yeah, very interesting work. I think, the data format these days is definitely very important, especially, given the ISO error comparison, it
Yeah.
shows significant improvement, right?
Yeah.
So yeah, any questions from the audience? Daniel, want to add a
Yeah.
question? Would you mind come closer? So it might be a little bit So my student Daniel has a ASPOS 26 paper. We're gonna
Oh,
present it pretty soon. So
congratulations.
yeah,
Thank you.
thanks.
Yeah, I
Yeah.
think the acceptance rate is very low. I heard it's like 10% or something.
Yeah. So yeah, Daniel, go ahead.
Thank you for the great talk.
Thank you.
Um, so a large majority of your presentation seems to put emphasis on designing, hardware for the or well, targeting workloads that are reducing bit widths, which seems to be the common trend. We have a lot
Yeah.
of optimization.
Yeah.
But something that I've noticed is it seems that like model designers are still very how do I say it, restrained from reducing bit widths, even if, we have quantized models that show that we can reduce bit widths without losing a lot of complexity. It seems like a lot of models still run in like FP16 that are generally open source on like Hugging Face and whatnot. Do you how long or do you think will model designers finally start to slowly reduce model size to these like, quantized integer based smaller compact models?
Yeah,
I know
that's a very good very good question. So first, I can tell you some industry trends. So yeah, because yeah, quantization is very important. I think eventually people will converge to at least use FP8 for all the models, if possible. Yeah. So first, I think I mentioned at the beginning of my talk, if you go to look at the specification from Rubin Vera. So originally, if you look at also Blackwell and Hopper, you will notice that the throughput of FP8 data path, or maybe FP4, let's assume FP8 in Hopper and Blackwell, they are usually 2 times higher than the FP16 or BF16 throughput in the tensor core. So this 2 times number is because the precision is reduced by 2 times, the register bandwidth is reduced by 2 times. So that's why the throughput of FP8 is 2 times higher than FP16. But if you go to look at the specification of Rubin Vera, the FP8 throughput is 4.375 times higher than FP16. I don't know why. I cannot tell why using evidence, but my assumption is that first, NVIDIA is believing that because of the success of DeepSeek V3, it believes that as all the future, or most of the future AI winners, they will switch to FP8 training and FP8 inference without accuracy loss. So that's why basically NVIDIA is forcing you to use the FP8 tensor core at least. Because if you don't use, I mean, with the same Rubin Vera GPU cluster, your throughput will be 4.375 times lower than your competitors, which is very bad.
Yeah.
Yeah, you cannot tolerate that basically, in my opinion, when you do large scale pre-training. So this 4.375 times, in my opinion, is because in that, let's assume 4 times maybe. So 4 times is because that NVIDIA is cutting the throughput of FP16 data path by 2 times, right? Because originally there's a 2 times difference. Now it's a 4 times difference. It means that I'm cutting the FP16 throughput by 2 times compared to my original design, right? Then it's 4 times. So then the reason is 4.375 times. Eventually, I think it's because also the frequency is limited by the power actually. When you have a higher operating frequency, your power is higher. But if you use a low precision arithmetic, your energy cost is actually not 2 times lower. When you use FP8, I believe the energy cost is definitely more than 2 times lower compared to FP16 Mac units. So it means that you can increase the frequency of the FP8 tensor core. That's why I think it gives you this weird 4.375 times number for FP8. And if you use NVFP4 for training, the throughput will be 7.5 times higher than FP16. And in that case, will you consider use quantization? I guess yes, right? If not, then yeah, just you will consume maybe 4 times cost when training a model compared to your competitor. If you have billions of dollars for free, you can do that, but I guess most companies will not do that. So that's my first observation. The second observation is that although these are open source models, they are usually FP16. I think it's mainly because of the complicated infrastructure for inference. Even you use FP8 for training, you still need to handle the complicated like rescaling, dequantization, and some operator in FP32. You need to have customized the CUDA kernel, which is unlikely to be open sourced. I mean, if I am a model vendor, I have my own very efficient FP8 GEMM kernel. I don't want to open source it. DeepSeek has an open source one, but if you just get it, you cannot easily deploy it. Right, because yeah, like I think you need to set up a lot of different things. It's very complicated to just run a quick prototype experiment. So when we run prototype experiments, we still prefer speed. We want to publish paper fast. That's why I think we prefer FP16 baseline model. But if you really want to deploy a model and you don't use FP8 quantization, I mean, I don't understand why. But even you have some accuracy, or maybe for some very sensitive model, you can also choose to quantize a part of the layers in to FP8, right? I mean, in the worst case, your whole model is FP16, but you can still quantize some very insensitive layers to FP8. You can still get some performance and energy benefits. And I can say that, for example, for Tesla, like Tesla self-driving car, if you go to read the specification of the Tesla self-driving car chip, it almost uses 8-bit, always use 8-bit integer for inference. And if it cannot use 8-bit integer, it will switch to 16-bit integer, because the integer arithmetic is more energy efficient compared to FP16. And for this Tesla self-driving car, it's definitely a very strong edge application. So you have only one single user, like one car, one driver, during the inference, and you want to maximize your performance under the power budget of your chip. So yeah, so that's why I think quantization will be the future. Yeah.
Okay. Thank you for your insights.
Yeah.
Okay,
Thank you.
cool. So any other questions from the audience? You can, if you don't want to speak, you can type in the chat. Yeah, then we can probably have another two questions. I think it's already a little bit over time, but let me ask you one question. So I
Sure.
saw that you're trying to keep the attention score like in FE8, right? Then later, let's say when you are doing the nonlinear operations like softmax, are you converting them back to FP16 and do them in the MPU?
That's a good question. So here, like first, there's no flash attention involved. Like I think I always got the question like if you use this kind of quantization, what about flash attention? Because it divides the attention score in tile. But for this scenario, it's only for decoding. For the preview, I don't care. It's on NPU. I only use PIM to do decoding. For decoding, the attention score is just a few vectors. There's no memory over like a footprint, even no percentage breakdown for the turn score if you want to do the memory footprint breakdown. So here is like we only do this FP8 quantization after performing the softmax because
I see.
yeah, it's after the softmax it will, if you go to read the Hugging Face code of the Llama or Quinn, the softmax is computed in FP32 to ensure numerical fidelity. But after computing the attention score, it's actually called attention weight in the code. It will be simply downcasted to FP16. So you compute the softmax in FP32, then you get the results in FP32, but you are just downcast this FP32 number to FP16. Then you can, if you want to deploy the P3 the code to P3M for assuming that it can be commercially available, then like you simply run this FP16 attention score, runs the least significant Mantissa bits, then you get this value. Then you use this to do the attention score times value cache. Yeah.
Yeah, that makes sense.
That's procedure. Yeah, that's a procedure.
Yeah, in our ASPLS 26 paper, we call it Mugi. In our Mugi paper, what we did is that we approximate the input to the softmax. So you are approximate the output of the softmax, right?
Yeah.
Yeah, I mean, we don't have, I don't think we are showing that kind of close result to other frameworks because I think rarely people do the input approximation. So we also have slight increase in the resulting perplexity. So I think it's kind of on par with what you have. So probably, I mean, we can chat later more if we see, okay, whether we can, put them together and do something interesting.
For this one, if you only consider the turn score alone, like you maintain weight activation, keep it cache in FP16, we have some optimization study, but if you only quantize the turn score using this FP8 E4 M4 during the decoding, I think based on my experience, there's no perplexity loss.
I see.
Yeah, because and also like from if you want to do it for the for like for commercial deployment, maybe for self-driving car, you can always use the bit stereo implementation. Like you can like do this twice. Then you have, for example, you want to quantize this to E4 M8. Then you can just do this E4 M8 attention score using 2 cycles by using the same hardware. That's actually what's original integer people do. Like they have 8 bits integer MAC units. Then if the accuracy cannot be met, they switch to int16 by using the like kind of bit serial, but it's like coarse grained bit serial processing. They just process the 8 bits part of the int16 using 2 cycles with int8 hardware. Yeah.
Right. That makes sense.
Right.
Yeah, cool. Yeah, it seems we didn't receive more question from the chat. So yeah, so probably I think that's already 7:10. It's yeah, let's thank the speaker once more. And yeah, very exciting talk.
Yeah,
And
thank you.
yeah, then look forward for future interaction with you. Okay.
Sure. Yeah, if you have further questions, you can just contact me through email. I mean, the audience, just send me an email. And also I have a website. I didn't put it here, but again, like this P3M is available on GitHub. I think currently only the quantization algorithm is available, but I guess I may open source more things if the paper is accepted. But it's available on archive. Yeah.
Yeah, definitely. Yeah, thank you so much. Yeah, let's thank the speaker once more, and I will look forward for the future talks. And yeah, I will probably catch up with you later. Okay.
Okay. Thank you, Prof. Wu. Bye.
Bye.